The presentation introduces our paper, Supporting Guided Exploratory Visual Analysis on Time Series Data with Reinforcement Learning. This work is in collaboration between Intelligent Big Data Visualization Lab and Huawei Cloud. To understand new time series data, exploratory visual analysis stands out as a preferred method that involves identifying questions of interest, investigating visualized data, and formulating hypotheses. However, conducting EVA on time series data is challenging for its target users, who are typically experts in their domain but novices with regard to visual analytics. Prior research in EVA for time series data has focused on computational analysis or visual representation. However, few attempts have been made to provide guidance on walking users through the process of EVA. To automate guided EVA for time series data, two challenges need to be addressed. The first is goal unclear. Typically, an analyst starts EVA without a clear exploration goal until he or she learns more about the data. Thus, interesting data insights should be automatically extracted and recommended to users, providing a first glance at data and helping develop a clear goal. The second is path unknown. The path leading to the desired goal may also be unknown to the analyst. Thus, it is important to provide the analyst with step-by-step EVA suggestions that help determine which parts of the data to explore. To address the above challenges, we developed VIS, a reinforcement learning-based system to support guided EVA on time series data. Here is a demo of VIS. As a user uploads a time series dataset to VIS, it is displayed in the timeline view. In this view, the user can explore the raw data by scrolling through different variables and selecting a specific time interval. The user can also manipulate the exploration parameters such as the variables and the time range. Once the parameters are set, he or she can click the Start button to check the result of an EVA sequence, which is presented in the sequence view. In the sequence view, the user can add, delete, or exchange insights. If the user is satisfied with the results in the sequence view, he or she can click the Export button on the top right corner of the timeline view to export the final EVA sequence. Next, I'll introduce our methodology. First, we collaborated with a database team to understand how data analysts conduct open-ended EVA of time series data in practice. By analyzing the findings and challenges derived from the interview, we identified a set of 4 design requirements, including DR1 to DR4. Then, we collected relevant examples or cases to understand insight types that frequently emerge from an exploratory analysis of time series data. As a result, we collected 80 EDA notebooks from Kaggle and identified 8 insight types and their co-occurrence relationships. Next, we shaped the generation of EVA sequences into a reinforcement learning problem to address DR2. An EVA sequence can be regarded as a sequence of small, incremental steps while at each step, analysts take a data-driven action. Given its characteristics, we model the generation process of EVA sequences as a MDP model. The first part of the MDP model is the state. A state describes all the insights the agent explored from the first step to the nth step, which constitutes an EVA sequence of length n. An insight space I includes all the insights from a given time series dataset, while a state space S enumerates all the possible permutations of the insights from I. The insights in the state space is defined as a 6-tuple. The first 4 items constitute metadata which describe the data patterns characterized by an insight. The latter 2 items constitute value, which capture the temporal relationship of time series data covered by the insight. From the current state, the agent selects an action to discover a new insight, which constitutes the latest insight of the next state. The action space lists all the possible actions to explore new insights from time series data. To formulate the action space, we referred to the metadata of insight. The new explored insights differ from the current insight by one element of the metadata, with each corresponding to a specific analysis behavior. After obtaining a new EVA sequence, the environment returns a reward calculated by the reward function to inform the agent how well the EVA sequence is generated through. Rewards can be designed by balancing familiarity and curiosity, where familiarity emphasizes the association between 2 consecutive states while curiosity encourages the discovery of unknown states. Based on the formulation and the design requirements, the pipeline of our system was designed to include 3 main modules: segmentation, generation, and representation. The segmentation module first partitions a given time series into multiple time subsequences based on its characteristics. Such time subsequences serve as the basic units for extracting insights. The module then selects a specific time subsequence and extracts its corresponding insight to form an initial EVA sequence as the starting point for the generation. The generation module generates an EVA sequence by starting with the initial EVA sequence from the segmentation module. Then, at each following step, the module discovers a meaningful insight through the action predicted by the RL agent and appends it to the sequence to form a coherent EVA path. We represent a state as a vector through feature engineering and then feeds the vector into the RL agent. Regarding its metadata, type, subspace, breakdown, and measure are represented as vectors. To represent raw value in its value, we adopted casual CNN to represent raw value using fixed-length embeddings. Given the feature vector of the state, the objective of the RL agent is to select the most appropriate action to discover a new insight for the subsequent state. The agent consists of two components: the actor that predicts the probability of performing each action at the current state, and the critic that predicts the maximum expected return, which is the sum of expected rewards, when continuing to explore from the current state to the final state. First, the feature vector of state is fed into a shared LSTM-based encoder. The hidden state of the NTH insight is used as the unified representation of the state. Then, the hidden state is fed into the actor and critic respectively. The actor and critic have similar network architecture, consisting of multiple fully connected layers. Compared with the critic, the actor has an additional output layer consisting of two components, including semantic weight and mask. Semantic weight is used to indicate the logical validity of executing an action through the semantic relationship between insights before and after executing the action. The second component of the actor, mask, is used to avoid selecting actions that cannot be executed at the state. Last, the agent outputs two items: the action probabilities computed by the actor and the expected return computed by the critic. When training the agent, the goal is to make the cumulative reward obtained by the selected action as close to the optimal case as possible. Thus, we applied the loss function and utilized stochastic gradient descent to optimize the parameters. Such an insight-by-insight generation method also facilitates online feedback responding to user interaction by suggesting an update on the EVA sequence. The representation module shows each insight of an EVA sequence as an annotated chart along with textual descriptions, to communicating the generated results. The evaluation of VIS includes an ablation study, a user study, and 2 case studies. The ablation study evaluates the performance of the generation module through 3 comparative experiments focusing on the RL algorithm, LSTM-based encoder, and mask, respectively. The results showed that the mean returns of VIS is higher than other baselines. In the user study, we compared the quality of the EVA sequences that were generated by the RL algorithm, those generated by the RL algorithm without semantic weight, and those created by human experts. The results showed that there is no significant differences between VIS and human, but VIS performs significantly better than the algorithm without semantic weight. The 2 case studies asked domain experts to conduct visual analysis tasks on physiological measurements and BitBrain's datacenter traces, respectively. The first case study showed that VIS can provide effective guidance on supporting EVA on time series data. That ends my presentation.